we have seen how differentiation in time domain carries over in the transform domain by multiplication of f of s by s and adding on to it the information regarding the initial value of the quantity which is being differentiated. Let us look at an application of this. This application is important in the sense that the result that we are going to get here will be used over and over again in circuit analysis. Let us consider an inductor of L henries carrying a current I of t. Let the voltage across the inductance be VL. So, these are the two terminals of the inductor, and you have a current IT passing through L generating a voltage VL. The fundamental rule relating VL and IT in time domain, this is VL of t of course, VLT equals L times di dt. Now, if you know the Laplace transform of the current IT, then we should be able to find out the Laplace transform of the voltage VL of t using the differentiation rule that we have just now studied. So, let us Laplace transform the left hand side and the right hand side. Assume that I of t has the Laplace transform I of s. So, if you make the Laplace transform of the left hand side and right hand side respectively, and let VL of t have the Laplace transform VL of s, then we have VL of s equals L times the Laplace transform of di upon dt will be s times I of s minus I0 minus. So, we can write this alternately as Ls times I of s minus L I0 minus. Now, 2 points to be noted here. One, time domain quantities are given lowercase letters VL and I. When we make the Laplace transform of that, we use the capital letters VL of s and I of s. This is the convention. Secondly, we are interested in finding out VL of t starting from 0 minus onwards. There is a possibility that I jumps from 0 minus to 0 plus. So, if you want to take the derivative of that current, including the transition from 0 minus to 0 plus, then we must take the initial condition here as 0 minus. On the other hand, if you are interested in the behavior of VL of t from 0 plus onwards only, and you would like to consider all values of VL from before 0 minus to be 0, then we have to take this I as 0 plus. But we are going to illustrate this taking 0 minus values because that is a more general situation, and so optionally of course, as I said, you can take 0 plus as well. So, this equation tells us that if you know the Laplace transform of current I of s, you can calculate VL of s in this manner. But to do this, you must know the initial value of the current. We can invert this expression and find out I of s in terms of VL of s as well. So, if you do that, then I of s can be written as VL of s divided by Ls plus, because you are going to transfer this to the other side, you get I0 minus over s. So, that gives you an alternative expression relating the terminal current and terminal voltage in the Laplace transform domain. I of s is VL of s over Ls plus I0 minus over s. So, both these equations now are the terminal equations of an inductor in the transform domain. This is the terminal equation of an inductor in the time domain. These are the equations in transform domain. Both are equivalent to each other. Notice one thing, that the derivative operator is removed. These are purely algebraic equations. However, the extra term that you need to have here information is the initial conditions in the inductor. Now, provided the initial conditions are 0, suppose I0 minus is 0, there is a proportional relationship between VL of s and I of s. VL of s is Ls times I of s. IFS is VLS over LS. That means there is a kind of generalized impedance to the current flow in the transform domain. If a current IFS passes through an inductor, the voltage is LS times IFS. So LS can be regarded as the generalized impedance of the inductor in the transform domain. Same thing here also, VLFS over LS. So 1 over LS can be thought of as the generalized admittance of the inductor. The impedance concept, the proportional relationship between a voltage and current in whatever domain you are talking about, transform domain or j omega domain in the sinusoidal circuit state situation, are all valid provided you do not have these extra terms. That means if there are no initial conditions, there is a proportional relationship between voltage and current in the transform domain. These initial conditions spoil that character, but we will see how to take care of that later on. Now this particular equation can be represented by means of a circuit representation like this. We have an inductance, we can think of that having a generalized impedance LFS, and we have a current passing through it, not the raw current but the transformed current, the Laplace transform variable, and across the terminals of the inductor we must have a voltage VLFS. So this is the voltage across the terminals of the inductance. We know that VLFS is LS times IFS minus LI0 minus. So this current IS passing through LS will develop a voltage which is LS times IFS in the transform domain. But to complete the picture we must have an additional term here, minus LI0 minus, and this quantity is independent of IFS. So LI0 minus is independent of IFS, therefore there must be an extra voltage here which is independent of IFS, that is equivalent to a voltage source. So you must have a voltage source in the transform domain which is L times I0 minus like this. So this description answers this equation, that is this circuit VLFS can be thought of as IFS passing through LFS developing a voltage LS times IFS plus minus LI0 minus, because this is a drop followed by a rise. Similarly, if you want to model this equation by means of an equivalent circuit representation, we have an element having a generalized impedance LS with a terminal voltage VLFS. So naturally the current here will be VLFS over LS, but the terminal current IS is larger than this by an additional value, therefore you should have a current source which is I0 minus over S. So the sum of these two currents will be your terminal current IFS. So this then is another equivalent representation of an inductor in the transform domain. We have an inductor having generalized impedance LS in parallel with a current source of strength I0 minus over S in the transform domain. This is the terminal relation. So you have two equivalent circuits for an inductor which incorporates the initial value of the current also in the transform domain. Both these are called transform diagrams. Transform diagram pertaining to an inductor. One incorporates a voltage source, the other incorporates a current source. So depending upon your convenience in the circuit analysis problem, if you favor the use of a voltage source, we use this. On the other hand, if you are in love with a current source, you can use this. In particular, if you have a network in which the node equations are preferred, the preferred method of solution, maybe you would like to have a current source, but both are equivalent. The important thing to keep in mind is that if the terminals of the inductor in the actual circuits are A and B here, the terminals in the transform diagram are these A and B. We should not think that the terminals of the inductor in the transform diagram are these two, because the totality of the structure here represents the inductor carrying an initial current. So that is to be kept in mind. What we have done here is representation of an inductor in the transformed domain, where the variables in the circuit are the transformed variables, not the functions of time. This is the Laplace transform of the voltage, this is Laplace transform of the current. So, the variables are transformed variables, and the element strength is Ls. This is called the generalized impedance of an inductor in the transform domain. The generalized impedance of an inductor in the transform domain is Ls. In a similar fashion, we can give similar representations for a capacitor with an initial charge on that. That we will postpone a later time. We will not do this in great detail at this point of time. Just as we have a generalized impedance Ls for an inductor, for a capacitance it turns out that the generalized impedance is 1 over Cs. We will do that later. But our point in presenting this at this stage is to show an application of the derivative rule in the Laplace transform theory, how we can apply that to evolve circuit models of this type. These are called transform diagrams. So, we have a transform diagram of a whole circuit. We have similarly generalized impedances for inductors, capacitors, and so on. The whole assembly is referred to as the transform diagram. This is the transform diagram pertaining to one element, which is an inductor. So, after having considered this, we will now go on to study the third property of the Laplace transformation, multiplication by t. So, we would like to ask the question, what is the Laplace transform of t of t? This is the question that we would like to ask. So, the Laplace transform of t of t 0 minus to infinity t of t e to the power of minus st t. This is what we would like to ask. Now, to do this, let me take d by ds of f of s. Suppose I want to take the derivative of f of s, which is the Laplace transform of f of t. This is d by ds of 0 minus to infinity of f of t e to the power of minus st dt. This is f of s. The integration is with reference to t, and we are taking the derivative with reference to another variable. So, we can introduce this inside the integration sign, and this can be written as 0 minus to infinity of f of t d by ds of e to the power of minus st dt. And this, when you take the derivative of this with reference to s, you get a minus t sign outside. So, 0 minus to infinity of, I will put a minus sign because of that, t of t e to the power of minus st dt. And that is exactly what we are having here, 0 minus to infinity t of t e to the power of minus st dt, and that integral is equal to minus d by ds of f of s, as we can see. So, this integral is equal to minus d by ds of f of c, because it is negative sign. Therefore, this will be minus d by ds of f of s. So, when you multiply a function of time by t, as far as the transform is concerned, it is equivalent to the negative of the derivative of f of s with reference to s. So, you can see that there is a nice arrangement here. You multiply by t, you get minus d by ds of this. On the other hand, when you take the derivative of f of t df by dt, you are multiplying that by s, s f of s. In the derivative formula, you get d by dt of f of t has the Laplace transform s times f of s. On the other hand, when you multiply t of t, it is d by ds of f of s, except for this negative sign, it is somewhat a dual relationship exists. Now, based upon this, let me extend this result. Suppose I take t squared f of t, then t f of t is minus d by ds of f of s. Therefore, I must write minus of d by ds of the Laplace transform of t of t, which is minus d by ds of f of s. So, this will be minus 1 squared d squared by ds squared. That is how it will be. So, you have T n f of t, it turns out to be, if you take Tn, you have minus 1 raised to the power of n, the nth derivative of f of s. All the time we are assuming that these are causal functions. What if I write T n f of t, we assume that T n f of t will be 0 for negative values. So this is understood. So let me take simple example. We know that u of t has the Laplace transform 1 over s. Now what happens if I take the Laplace transform of t u t? I multiply this by t, then you must take the negative or the derivative of this with reference to s, minus d by ds of 1 over s, and that is 1 over s squared. And t u t is indeed r t. So the Laplace transform of a ramp function is 1 over s squared. So we can write the extend our Laplace transform pairs, the table. We have already considered u of t, delta t, sin omega naught t, cos omega naught t. We can also say r t Laplace transform is 1 over s squared. Now suppose I take t squared u t, this is t u t of course, t squared u t, that means you must take this derivative of this once again and attach a negative sign. So if you do that, it is minus 2 over s cubed will be derivative, and you attach a negative sign, it will be 2 over s cubed. Continuing in this fashion, suppose I have t cubed u t, then it will be, again you take the derivative of this, it will become 3 times 2 divided by s to the power of 4. And if you proceed further in this fashion, if you have t n u t, then you have n factorial over s to the power of n plus 1. That is how it goes. As we take higher and higher powers of t, the Laplace transform goes in this manner. Okay. Let us now consider another example. Suppose I have e to the power of minus alpha t u t, then we know its Laplace transform is 1 over s plus alpha. Now suppose I multiply this by t, e to the power of t times e to the power of minus alpha t u t, then its Laplace transform is minus d by ds of 1 over s plus alpha, and that is indeed 1 over s plus alpha whole squared, 1 over s plus alpha whole squared. And suppose I have t squared e to the power of minus alpha t u t, then it can be shown that this is indeed 2 over s plus alpha to the power of 3. And in fact, as before, you have t to the power of n e to the power of minus alpha t u t. You continue in the same fashion, you have n factorial over s plus alpha raised to the power of n plus 1. That is how it goes. So in other words, we need not remember the Laplace transforms for t multiplied functions like this, either e to the power of minus alpha t or in terms of u of t. It is enough if you know the basic formula for u t, then whenever it is multiplied by t, t to the t square, t cubed, etc., then you can easily derive them without any difficulty. Let me now take the next property, which is the integration, which is again very important and which commonly occurs. Let me consider f of t dt indefinite form, which we can always regard this as 0 minus to t of f of t dt plus, suppose this f of t is a current, let us say, then what we are doing is by integrating you get the charge. So we often find it convenient to consider the charge at a function of point of time t as the initial charge plus the additional charge that is carried by the current in the point from 0 minus to t, in the interval 0 minus to t. So, this is the value of the integral between the definite limit 0 minus to t plus the initial value of this integral. We will write this as f inverse minus 1 within bracket 0 minus, that is, this is the initial value of this integral plus the addition to the integral in the value in the interval from 0 minus to t. So, this is how we can put the indefinite integral in the form of a definite integral plus the initial value. Now, in order to find the Laplace transform of that, let us find the Laplace transform of these two individual quantities. So, 0 minus to t of f of t dt, suppose I call this g of t, then we know straight away that g0 minus is equal to 0, because we are taking the integral between the two limits, same limits 0 minus to 0 minus, it must be 0. And further, let limit as t goes to infinity of g of t e to the power of minus st equals 0, because we are taking the value of g of t to be Laplace transformable, and we are taking the value of real part of s is such that this tends to 0. That means the value of s is within the region of convergence of the Laplace transform of g of t. With these conditions, and further we also know that g prime t, the derivative of g of t, is f of t. G prime t is f of t, because this is the integral of this. The fundamental rule of integration tells us that the derivative of this is going to be f of t. Using this, the Laplace transform f t dt, Laplace transform of that equals 0 to infinity of this quantity, which is gt e to the power of minus st dt, and that would be obtained as, let us do this integration by parts. I will take g of t e to the power of minus st, I take the integral of this divided by minus s between 0 minus to infinity, plus 1 over s 0 minus to infinity of e to the power of minus st g prime t, the derivative of g of t times e to the power of minus st dt. And this will be at the upper limit, this will be 0, because limit as t tends to infinity of g to the power t e to the power minus st, this is 0. At the lower limit, this is also 0, because g of 0 minus is 0, therefore this is 0, and you have 1 over s of g prime t is the same as f of t, therefore 1 over s times f of s. So, we have that the Laplace transform of this is f of s over s, and this is a constant. F, the initial value of the integral is going to be a constant, that will be the Laplace transform of this is f initial value divided by s, and the Laplace transform of this is f of s over s. So, we have Laplace transform of the indefinite integral f t dt as f of s over s plus the initial value of the integral at 0 minus over s. On the other hand, if you want to take the Laplace transform of the definite integral 0 minus to t of f of t dt, that means the initial value of the integral is ignored, then this is simply f of s over s, f of s over s. That these are the two important results relating to the integration, and we can make use of this when, suppose I have a capacitor value C, and this is the voltage across the capacitor VCT, and the current to the capacitor is IT, then we can write VCT is 1 over C, the integral of the current, which is the charge on the capacitor. I can write this further as 1 over C 0 minus to t of I dt plus the initial charge on the capacitor 0 minus. So, if I take the Laplace transform of the various quantities, I have Vc of s, the Laplace transform of the capacitor voltage, is 1 over C, this is IFS over S plus a constant, this is a constant Q0 minus over S. So, I can write this as IS over CS plus Q0 over CS, which is IS over CS plus Q0 minus over C is the initial value of the voltage across the capacitor. Therefore, I can write this as Vc0 minus over S. So, this equation can be represented nicely in this fashion. This is the Laplace transform of the current, this is the Laplace transform of the voltage across the capacitor, and this is the generalized impedance 1 over Cs. Is passing through 1 over Cs will create this voltage drop. In addition, I have the initial value of the capacitor voltage divided by S, a voltage source. So, this is then the transform diagram of a capacitor. In the same way as we have derived it for the case of an inductor. An equivalent in the term in the parallel form in a capacitor in parallel with a current source can also be derived. I will not do that, it will leave it as an exercise for you, that it can be drawn up in a similar fashion as we did in the case of an inductor. It is very important now to see that you must distinguish between these two formulas, and when you have an initial charge on the capacitor as we have, that is equivalent to a source here, which is the represents the initial charge on the capacitor or the initial voltage across the capacitor. So, we will stop this discussion on the properties of Laplace transform at this point. So, in this lecture what we have covered is, to start we started off with a review of the definition of the Laplace transformation and the type of functions which are Laplace transformable. Then we went to discuss the various properties of the Laplace transforms. In particular, what we talked about was the linearity property. Then we talked about the derivative, how the derivative of a time function carries over in the transform domain. Then we discussed how multiplication of f of t by various powers of t, how such functions are transformed in the Laplace transform domain. In particular, we said t of t has a Laplace transform minus d by ds of f of s. Then we went to the integration of the time functions, and we distinguished between the definite integral and the indefinite integral, and in both the derivative case and in the integral case we saw how they can be applied to the situation of a inductor and a capacitor, how the relation between the transformed variables of currents and voltages across inductors and capacitors can be represented by means of certain diagrams which we called transform diagrams. We will continue the discussion of the properties of Laplace transforms in the next lecture.